In the previous video, we talked about the derivative of the exponential function. It turned out that e stood for easy. The derivative of e to the x simply is e to the x. Don't forget to multiply, of course, by the derivative of the argument. That would be chain rule, which is important. Now we're going to talk about integrating exponential functions. And I think we'll start by reminding us as to what the derivative of an exponential is, which again is easy. Let's start with that. So I want you to recall that the derivative of an exponential function is just simply itself. That should lead you to the conclusion that if I integrated an exponential function, what would I get? Well, I'm thinking of an original function whose derivative is e to the x. That's what integration actually says. Guess which function we're thinking of? E to the x, of course. So derivatives of exponentials are easy. Integrating exponential functions also quite easy. E for easy. But there's a little more to it than that. If this was the only exponential function we had to integrate, well, certainly that's what we would get. But what would happen if I integrated e to the x squared? Let's say times x. What would I do? Well, I need you to remember integration by substitution. Now, if you integrate using substitution, or actually even the key method, you might say this. You might say, I have a complicated function, a composite function. And typically what happens is the outer function gets integrated and only the outer function. So I think of the integral symbol as staring at this e and saying, e for easy, the answer is e to the x squared. There's nothing more to do here. But wait, it's a product. The product says, well, wait a second, before I can do this, what I need is my key. I want you to imagine it's locked up tight. You're not allowed to do it yet. So what is the key? The key is the derivative of the inner function. Now, what is the derivative of my inner function on this problem? The inner function is x squared, and the derivative is 2x. Now, in order to proceed, I need to see the key, and the key has to be right here, and it's not there. Can we reconcile with that, though? Can we force the issue and make the key sit right where it should? Absolutely. What you end up doing is planting a number 2. We'll call that our planting of evidence. We counter on the outside with a 1/2. This would be the counteracting feature. And then you circle the key because it's precisely correct. And what is the key after all? The key is nothing more than permission. Permission to do what? Integrate the outer function only. So the 1/2 is a survivor. The integral of e to the something is e to the something as long as I have permission, which that's what this is. And then plus c. You don't get an x, you don't get a 2x, none of that. You just get the integral of e to the something being the easiest function in calculus because the integral is itself. Now, there's certainly another way to do that, and that's the formal approach. And the formal approach is where you select a u and you take its derivative also. So let's repeat this problem. Now, the most important thing to get started on a problem like this is your choice of u. And the guidelines tell you that u equals inner is always a good choice. So u equals inner, u equals x squared is a good choice. That's my inner right here. And this is my outer. Inner meaning the argument, really. E is the outer function. E to the something, what is that something? X squared is the inner function or the argument. We'll deal with this later. In fact, we may not even need to deal with that. Autopilot, du. Take a derivative. That's 2x. And it's du dx, so move the dx over. That's an important part of it. Make sure that dx is there. Divide both sides by 2. And we just learned that du over 2 is precisely the same as x dx. Well, that's going to be very, very helpful to me because x dx is right there. So integrate e to the u, because that's now u right there. X dx is du over 2. The 1/2 comes out front, and you are left with perhaps the easiest integral problem that we have in math. And that's integrating e to the u du, or e to the x dx, because it just is itself. I mean, I really integrated. I always say don't forget to integrate. I didn't forget to integrate. It just so happens that the integral of e to the u is e to the u. And don't forget to replace u with what it used to be. It used to be x squared. Well, that does look familiar, doesn't it? Because that's the answer we got using the other method, which was the key or evidence method. See, we got the same result as before. So I do prefer u-substitution because it's a much more formal method, and the guidelines say u equals inner should lead me to my result, and they often do. And now I'm going to provide you with a really good demonstration of why I keep calling it a guideline and not a rule. There isn't a rule that says u equals inner. It's a guideline. It's a suggestion. There may be other u's that work. Check this out on this problem, because there is another u that works. So I'm going to start over again. I've got the integral of e to the x squared times x dx. And I'm going to actually do something a little different than the guidelines. What if I decided, and this is unusual, we don't normally do this. What if I decided to make u equal the whole thing over there? All right, I'm going to try it. U equals e to the x squared. Let's try it. Now, what is du dx, guys? Du dx is a very careful derivative. We check off the e because e for easy is just itself. We check off the x squared because the derivative is 2x. We move the dx to the other side, and you get du equals e to the x squared times 2x dx. Now, I don't see any 2's up there, so let's get rid of that 2 first of all. And so I have du over 2 equals e to the x squared times x dx. Wow. Look at this. That box is the whole problem. We've never seen that happen before. So that's a really good match, actually. It's a very good match. So check out the connection between our original problem and du over 2. It's the whole thing. So instead of putting a u here, I'm actually just going to grab this whole thing and call it du over 2. Apparently there is no u left. This whole package gets replaced with du over 2. Okay? That's a pretty dramatic result right there, because the 1/2 comes out front, and I'm simply integrating du, and we remember what happens when the antiderivative touches d for derivative, you actually get the u. So it's looking to me like we're getting a different answer, except when you go back and replace u with your choice of u. And for this time, we chose u to be e to the x squared. We've done this problem 3 different times, 3 different ways, and we keep getting the same result. So it's interesting to note that there are other ideas out there for the choice of u. There's not just one choice. There's different choices. Your u could be a little different than mine, and it still could work. But the guidelines usually say u equals inner is going to point you in the right direction, and it often does. Okay. So let's take a look at a few more examples of integrating an exponential, and just noting that integrating e to the u is just e to the u, so that's a nice easy result, but oftentimes these can get a little more involved. So let's integrate e to the, how about 2x cubed plus 1 multiplied by, how about 4x squared dx? Can we do this problem? Well, remember, the best choice for u is actually the inner function. I think that's probably your best choice, because then du equals just 6x squared dx. Now, I got a problem here. I got a 4x squared dx. I'm trying to match with a 6x squared dx, and that's just not going to work. So let's take the 4 out front. So the integral becomes 4 e to the 2x cubed plus 1. And now it says just x squared dx, which I can now get a match because I can divide this by 6. So the box of x squared dx is right here, can be replaced with du over 6. So what's this going to look like? 4 e to the 2x cubed, well, that's all going to be rewritten as u now. And this box became du over 6. We can slide that 6 out front, and if we do that, we get 4 over 6, integrate e to the u du. So no matter how tough the problem seems, we can always land on this. Well, 4/6 is 2/3, and the integral of e to the u is e to the u. And so the answer would be 2/3 e to the, well, u. You got to put u back. So it's really just u-substitution, I suppose. And u equals inner is still working. So now it's also good to know that the integral of e to the u is just e to the u. Integral of e to the x is just e to the x. But the integral of e to the x squared is not e to the x squared. And the reason is you don't have permission to do that. Permission is the derivative of the inner. So the derivative of x squared is 2x. There has to be an x over there to really make the problem work. So be careful. You can't just integrate e to the x squared and call it e to the x squared. Let me demonstrate. Integrate e to the x squared. There are those that would say the answer is e to the x squared, but I will tell you that it is not. That's not the answer. Let's try u-substitution. U equals x squared. Du is equal to 2x dx. All right. So let's do our substitution. Antiderivative of e to the u. Here's my problem. Look what's left. It's a dx. And what's dx actually worth? It's worth du over 2x. I mean, you can bring that x over there, and that is just not looking pretty. Now, the 2 can come out front. I get that, but look what I'm asking you to integrate. I got a lot of problems with this. Number 1, the variables do not match. That is a problem. The variables do not match. Secondly, it's a fraction. I can't do fractions of any kind right now. So that's a problem too, unless it matches the natural log pattern. Well, first of all, the variables don't match, so there's no sense in even trying that. Well, I might be able to do something about this x. Come on over here, and we realize that x is equal to, well, plus or minus the square root of u. So which one do I use? You know, that's a problem in itself. But let's just pick the square root of u. Well, at least you've got it in the world of u, but you've got this nasty fraction. Can't do that. We cannot integrate a fraction like that. So we're really, really stuck. I don't know what to do about that problem. So you got to be really careful. It seems like integrating e to the anything just becomes itself, and that is just not true. By running u-substitution, you realize that you know, that stuff on the right side there better disappear. And sometimes I need things on the right side, or I can't even do the problem. Let's try a few more. Let's try a few more. Let's find, well, let's do an integral first, a definite integral, and then we'll get area beneath a curve. I want you to really look carefully at this problem. Now, the reality is we're not supposed to be able to integrate fractions. We're not supposed to integrate quotients. There is no quotient rule. There's only really 2 things you can do. One is you can push it to the top. That works. And the second is you can say, maybe this is a natural log. You remember? We used to integrate fractions and they became natural logs. Now, if it's going to become a natural log, it has to pass the three-step checklist. So let's try the three-step checklist on this one. Number one, are you a fraction? Absolutely. Number two, is the denominator to the 1 power? Nope. So you can stop right there. This is not a natural log. So that didn't work. So the only other option I've got is push it to the top. That's all I got. So let's push it to the top. Now when you push this to the top, it becomes x to the negative 2, correct? Also, 1 over x can be written as x to the negative 1. That's what it is, x to the negative 1. All right, u-substitution. I hope it works. U equals inner, right? Inner meaning the argument. Autopilot, take your derivative, du dx. Okay, now derivative, the negative 1 comes down and we deduct 1 from the exponent. Got it. I'm beginning to like what I see. Look at this and look at this. All you have to do is divide both sides by minus 1. And I realize now that negative du is x to the negative 2 dx. Isn't that convenient? That's very convenient, in fact. So let's integrate. From now on, this is e to the letter u. From now on, this is negative du. Isn't it funny how we keep running into this particular problem, which really is the easiest integral in calculus? So minus is along for the ride. This becomes e to the u plus a constant. But what was u again? Oh, u was 1 over x. And we're done. So even though that problem seemed really challenging to you, even though it seemed challenging, it really wasn't. It was actually a u-substitution problem, and u equals inner is what led you down the right path. Don't forget du dx. Don't forget to replace that box in the back correctly. And actually, I think every one of these problems has to become integrate e to the u du, which is exactly going to be e to the u. It's the easiest integral in calculus. So, let's continue. This time what I'd like to do is I'd like to try to get the area beneath a particular curve, and it will certainly be an exponential curve. Now this one's going to be a particular challenge. I would like the area from 0 to 1 on this unusual curve. Don't forget, every integral needs that dx over there. Now what? So, you know how I keep saying that the guidelines say u equals inner, u equals inner, u equals inner. What about the guidelines for a fraction? What about the guidelines for a fraction whose denominator is to the 1 power? We had a different set of guidelines for those problems, didn't we? So let's take a look at this particular problem because I'm starting to see that there really is a pattern. Sorry. First thing I see is number 1 on the 3-step checklist. Am I trying to integrate a fraction? I sure am. Number 2 on the 3-step checklist, is the denominator to the 1 power? Sure is. Number 3 on the 3-step checklist, does the derivative of the bottom live on the top? It sure does. Now, I can tell you this. If you pass the 3-step checklist, then don't forget the payoff. And the payoff is that the answer is the natural log of the denominator. That's what it should be. So by checking 1, 2, and 3 off, if you need to make a few adjustments to make step 3 work, usually that's where you would make the adjustment by planting and countering. That's fine too. But don't forget there's a payoff to this. If you can pass all 3 of these, I guarantee you that the answer is simply the natural log of the absolute value of the denominator. And we got to run that from 0 to 1. So that would be the natural log of 1 plus e to the 1 minus the natural log of 1 plus e to the 0. Now, do we really need absolute values? I don't think so, because these are already positive. So it's natural log of 1 plus e minus the natural log of 2. In fact, natural logs love to combine together, don't they? Subtraction on the outside becomes division on the inside, and this would be our answer. Now, we could also get an approximate value of that answer by using our calculator. So I'm going to do that now and figure out what that would be. Give me 1 second here to do that. There we go. So I want to do 1 plus e, and hold on a second here. I'm trying to get, there we go, e to the x. All right, so there's e. Let's add 1 to that. That's 1 plus e. Next step would be divide by 2. So I'll divide that by 2. And the last thing is take the natural log of that, 0.620. So this is approximately equal to 0.62, and that's the area beneath that curve. Three-step checklist. That checklist is not from this chapter, actually. It's the chapter about integrating and making natural logarithms. Three-step checklist. You're integrating a fraction. Denominator is to the 1 power. Just so happens the derivative of the bottom lives on the top. Perfect. That means the answer is the natural log of the denominator. Now, what if you forgot the three-step checklist? Let's try this again. Integrate from 0 to 1, e to the x over 1 plus e to the x. Now, one of the guidelines we've also learned, when it's a fraction, is to try u equals denominator. That was another option we had. Autopilot, we take our derivative right away. Okay? And watch this problem evolve. This is the part we would box up. So we would integrate, and the box I just discovered here is du, the whole thing. The bottom is just u. So what I got right now is 1 over u, and I got a du. Now be careful. If you change into the world of u, I recommend highly, in fact you must actually, if you put numbers here, you must change these into u's. So 0 goes in here, that's e to the 0 right there. That's 1 plus 1 is 2. 1 goes in here, 1 goes in there, and that's 1 plus e to the 1, or 1 plus e. But look at the integral we have. Integrate 1 over u is natural log of u. We know that. So this becomes the natural log of the absolute value of u run out from 2 up to 1 plus e. So we get the natural log of 1 plus e minus the natural log of 2. And we don't need the absolute values anymore because these are both positive. In fact, we can combine these together into one fraction. And I think we've seen this answer before, 0.62. So that's how you would do such a problem with u-substitution. A great way to do that problem. Okay. So let's try one more example of integrating and finding the area beneath a curve here. But honestly, I do want to look around at some of these other indefinite integrals, because there's some challenges in here. Let's go all the way to problem 105 and look at the challenging problems back here. 105 says integrate 5 minus e to the x over e to the 2x. Okay, three-step checklist. Maybe the three-step checklist passes because it's a fraction. That is correct. Number 2 is the denominator to the 1 power. Well, not really. Because really what's down there is an e to the x squared. But I suppose if you want to say that it's to the 1 power, you can always box it up and say that it's the 1 power, so I'll let that pass. I'll let that fly. But the question is the derivative of the bottom living on the top? Let's find out. Number 3. What is the derivative of the bottom after all? Well, E for easy, it just is itself. Chain rule, chain rule, chain rule, don't forget it. So that's really the derivative of the bottom, and you know what? No. Not only does it not look like the numerator, I don't think we're going to be able to fix that. So I'm pretty certain that this is not going to be a natural log. If I could pass step 3, I would say it's going to be a natural log of the denominator. It's not going to happen. So what do we do in this situation? I still can't do a quotient. Well, you could push it to the top. That's one idea. Or what about splitting the fraction? That's another idea. Certainly allowed to do that in algebra. We split fractions in algebra all the time. So yes, you can if you need to split the fraction. So what do we have here? We have a 5. We have an e to the minus 2x minus, subtract your exponents, please. Don't forget, when the bases are the same, you do subtract your exponents. That is correct, and this got pushed to the top. Can we do it now? Can we do it now? I think we can. And I'm going to use the key method on this one because there's 2 different integrals going on here. So we have this one. And we also have this one. I think the key method is definitely the right way to go here because it's quick. Do I have permission to integrate the easiest function in calculus? No, I don't. It's locked up tight. What is the key that should be there? What is it? Well, we know that the key to the problem is supposed to be the derivative of the argument or the inner function, which is -2, and it's just not there. So what I want you to do is plant the -2 in place and counter it with a -2 on the bottom. Now over here, it's the same situation. The key is supposed to be the derivative of the argument, the inner function, which is -1, and I should see my key right there, and it is just not there. So we plant the -1, and then we counter it with a -1 over here, usually on the bottom. So what do we have here, guys? A -5/2. What about this key? You circle and check off the key. You know that it's not part of the answer, right? That never makes it to the answer. Permission granted to do what you wanted to do in the first place, which is integrate e to a power, which just is e to that variable power. And that's done. Negative is positive. What do we do about this key? We check it off. It is never, ever part of the answer. All you got was permission to do what you wanted to do in the first place. The integral of e to a power just is e to that power. And we're done. So splitting the fraction paid off. Using a key, I think, really paid off to unlock the problem. And if you don't like the key method, you can always do u equals. For this problem, right here, u would be equal to -2x. For this problem, u would be equal to -x. Don't forget to take the derivative du dx. That's an important step as well. Okay. I'll leave you with this problem. I'm going to make this one up here. Let's make it 2x. Here and here. And I'd like to integrate this from 0 to pi over 8. Looks like a pretty challenging problem. However, u equals inner is a great guideline for this problem. And the inner function is tangent of 2x because this is the outer function, e, exponential function. Don't forget your autopilot, du equals dx, du dx. The derivative of tangent is secant squared. No change to that argument. And what's the component at the end that people often forget? One more derivative. Derivative of 2x is 2. Now, if I divide both sides by 2, I learn something, and that is that du over 2 is secant squared 2x dx. Isn't that convenient? Look at what that is. Apparently, this box reduces to simply du over 2. I think I'm beginning to like this problem. Let's do the full and complete substitution, guys. Full and complete. From now on, tan 2x no more. We call it u. From now on, this box, no more secants, du over 2. Let's put the over 2 part out front already. Make it nice and easy. Now, you want to save some time, you want to make this easy. We're transforming into the world of u. So why don't you change your limits of integration into the world of u? Because after all, we're trapped in the world of x over here. So when x equals 0, what's u? Equals tan of 2, 0. Tan of 0 is 0. That didn't change anything. When x is pi over 8, what's u? What's the tan of 2 pi over 8? Isn't that the tan of pi over 4? The tangent of 45 degrees is 1. Now I'm really liking this problem. Because now that we're completely in the world of u, there's no looking back. You don't need any of this other stuff. You can cover it all up. If you can get the answer to this problem, you have the answer to the original problem. Look how easy this is. E to the u du, that just is e to the u. Oh, let's not forget the half over there. And then we have to put a 0 and a 1 in. So what do we get? E to the 1 over 2, e to the 0 over 2, which is e minus 1 over 2, which is approximately 1.71828 over 2. And let's just see what that is. So just so we can finish up here. Okay, there we go. So I'm going to do e to the 1 minus 1. There's my 1.7828. Divide that by 2. So it's approximately 0.859. Now, if you don't believe that the answer to this, which is at 0.859, is actually the answer to that problem, why don't we throw it in Wolfram Alpha and see what happens? We'll actually get to see it, graph it. Oops. Upside down. Here we go. Let's take a look here. Wolfram Alpha, what we're going to do is integrate e raised to the tan 2x times secant 2x, that whole thing squared, from x equals 0 to x equals pi over 8. So let's let Wolfram think about that for a second. We should not only see the graph, but get the answer. Well, that number looks familiar right there. Now here's the graph, okay? And this is of this trig function with exponentials, secants, and tangents. And look what it says right here, e minus 1 over 2, 0.859. Pretty dramatic result. So I think what you can end up doing on these problems is most of them turn into e to the u du if you do it correctly. Some of them, they end up being 1 over u, like we had a natural log problem in there too. So things we look for, splitting fractions if we have to. Other things we look for, 3-step checklist. Number 1, it's a fraction. Number 2, denominator to the 1 power. Number 3, the derivative in the bottom lives on top. Boy, if that's happening, I can guarantee you that the answer of the integration will be a natural log. And if you want to use u-substitution on a problem like that, u equals denominator is probably your best guideline. So take a look at this chapter and definitely start working on the homework problems. Have any questions, certainly let me know. Thanks.